Oh, I should not be muted. So welcome to everybody. Hopefully now you can hear me. And let's share the things here. Let me see. Oh man, share. There we go. Yes, I noticed that the level was going up and down. So at least I didn't go like 10 minutes without noticing. Like what I did. Okay, so we have this. Then what else do I need? I think that's it. Uh, I can allow you guys to talk if you want, and that's it. Okay, so can I see myself or can I not see myself? Yes,
Hi.
there we go. Hi, Tobias.
Hi.
Hi, Mark. Okay, so let's see. Are there a bit of news? So I started reviewing all this with two sets of mathematicians. One that has experience in generalized probability theories and quantum logic, and another set of mathematicians that are more geometry, like they know about symplectic geometry or that stuff. So there was a small change in language on the axiom of entropy because he said that it was weird that I was first introducing the inequality and then talking about the I. So now it reads that there exists a universal function such that there is an upper bound. So but there hasn't been so far any like life-altering changes, which means things are stable enough, which pleases me. And so today we are, if there are no questions, we can start and looking at this section that basically shows how the entropy constrains the space a lot. And in fact, one of the things that I looked at in the past couple of weeks while reviewing this generalized probability theory, that there are some things that they are generalized probability spaces that are not ensemble spaces. So hopefully this ensemble spaces are a subset of generalized probability theory, but I don't know yet, and I'll probably don't know, won't know for a few months. So because I have to go through all their definitions and see exactly how they map or they don't map to what we are doing. Okay. So if there are no further question or comments, we can start looking at the entropic constraint of the space. So the axiom of entropy not only constrains the functional form of the entropy, but it also constrains the type of space we can have. Additionally, it rules out some spaces that would seem physically pathological. The entropic structure in general will constrain both the topological structure, making it metrizable, and the convex structure, making it embeddable in a vector space. The entropy is also responsible for all the geometric structure of the ensemble space. So this these are the two things that we're going to look at today. So in principle, if you just have a convex space, that is, you can do mixture. There are some cases that where this addition is not really inside a vector space. So there would be ensemble spaces that are not subsets of a vector space. At the beginning, I thought, how cool, there might be new physics there. And then I realized that one, they're pathological, and two, the entropy actually rules them out. It makes everything embed in a vector space, which is interesting. So this existence of the entropy function constrains the convex structure, and also it should constrain the topology. Makes him so the entropy is going to make that the limit actually always converge, that the space is Hausdorff. That part I still don't quite hasn't quite finished. So if anybody knows about topological and vector space and stuff like that, I'm certainly I certainly need some help. But what we're going to look at today, especially this is the vector space embedding. And then the other thing that we're going to see is something that I struggled for a year and a half to prove. So the question is, the real line is a convex set. If you take any 2 points and you make the convex mixture, you are inside, right? And so the idea is that this line can extend to infinity. So a convex set, in principle, could extend and go to infinity. And the question is, if I put an entropy, can I still have something that goes to infinity, or the convex set needs to be bound because the entropy must be within a minimum and a maximum? So at some point, when two things become too far apart, then the entropy inside becomes too high, and then you are sort of ruined. And it took me 1 year and a half to figure out what is the right trick to prove that, and that's what we're going to look at today. So the first thing is going to be the vector space embedding, the fact that all the convex structure that we have is secretly a vector space structure underneath. So the axiom of mixtures does not constrain the convex set to be a subset of a vector space. The axiom of entropy, however, does. To be specific, it is the first three properties of the entropy that constrain the space. And the first three properties were continuity, the lower bound, the strict concavity, and the upper bound. So the fact that you're sandwiched things in, it allows you, and the continuity, it allows you sort of to constrain how things have to map. So just in general, a convex space embeds into a vector space if and only if it is cancellative, meaning that if you have that the mixture of A and E with a probability P and a mixture of B and E with a probability P are the same for some P, then A and B are the same. So basically, if you mix something, if you mix two things with something else, and the result is the same thing, then the two things that you were mixing at the beginning were the same thing. And again, you can have a convex space where this is not the case, and we're going to have an example later. But the idea is that the entropy is not going to do it. So this is a proposition, and there is a theorem in this paper that states that a convex space embeds in a real vector space with essentially this is the linear combination, is the convex combination becomes the linear combination only if you have this property expressed in this different way. So basically, in this paper, this proposition is statement, this theorem is stated, it's proven with different notation. I didn't have time to adapt the proof and carry it over, and so we're just going to take it as that's the case, and that's basically it. So intuitively, what happens is that if you have this property, you can go back. You can basically say, I have a final mixture, I have one part, and I have a coefficient. I can reconstruct the one of the two terms. So it's kind of like you're moving one part on the other side and using a minus. So you're basically allowing for mixtures that go in the opposite direction, which means that you not only know how to go in the space, but you also know how to go out of the space. You can go outward toward the boundaries of the space. And that's what makes it that it's embedded in a vector space. All right. And that would be essentially the traditional thing. So now we have to prove, so if this is the case, we have to prove that all the ensemble spaces are cancellative. Or if for all ensemble spaces, this property is actually valid. And how we do that? Well, we have A, B, and E, such that the mixture of A with E and B and E are the same for some P, then A equals to B, and therefore any ensemble space embeds in a vector space. And so now we are going to go through the proof, because that's what we have to look at details to make sure that this makes sense, and interrupting at any point where this is not clear, please, because that's what we're doing. We're checking that this is clear. Okay, so let A, B, and E in E three ensembles such that for some P0 in 0 and 1, the mixture of A and E is equal to the mixture of B and E. So this is where going to be our starting point. First, we want to show that if this is true, then this is also true for any p that is inside the open interval between 0 and p0 included. Okay, so first we start knowing that it's true for one p, and now we want to show that it's essentially true for all the p's from p0s to 0 excluded. So if this is the case, we can set, since p over p0 is going to be less than 1 and greater than 0, we have that pa plus p bar e is equal to p over p0, and we take this and divide it by p0, and we are going to have some element e that is, okay, let me turn off WhatsApp because otherwise I get too distracted. I can't turn off WhatsApp. Ah, jeez. Oh, whatever. I'll have to figure out how to shut up instant messaging next time. Okay, so what we do here is we divide by p0. So this terms a is going to be the same, is going to be p0 over p over p0, p0. And then we're going to have the remaining part of e that is not inside this mixture. If we do that, then we can, since we know that this is equal to this for p0, we can substitute what we have in parentheses. And now we can multiply and resum, and then we have that pb plus p bar e is equal to pa plus p bar e. Okay, so this is the trick that we're always going to be doing. We know that something is true for some p. We multiply and divide by something. We make the thing in parentheses look like the thing that we know it's going to work. And then we substitute with the a with the b, and we go forward. That's kind of the technique. Now that we know that it's true for anything that is less than p0 but greater than 0, we want to show that this is also going to be true for any p that is strictly inside 0 and 1 without 0 and 1, 0 and 1 excluded. So since we want to be able to expand multiple times, we want to do this trick essentially twice, we want to be able to find a p such that the pa plus pa plus the remaining 1 minus 2p e, this is equal to pa plus p bar p0a plus p0 bar e. Again, so if we have this equality, we're going to be able to take this p, transforming in something that is a p0 that we know how to substitute, and then and do the same on the other side, right? So we want this, we want to find a p such that this is equal to this. And of course, we can now multiply the p bar with the p0 and the p0 bar with the p bar, and we have this expression. So we want this equal to this. The coefficient in the middle term on both sides of the equality then has to match. So we must have that p is equal to p bar p0. Okay, so that is we want p equals p bar p0, which now we just do some calculation. We have p equals p bar is 1 minus p, p0, then we just multiply and distribute. So we have p0 minus p0. And then we take p0 and make it explicit. So we take this and bring it on the other side. So we have p0 equals p plus p0. And then this is just 1 plus p0 multiplied by p. And now we can make p explicit. So p is equal p0 over 1 plus p0. This is the p that we're going to use to make our calculation. So now you say, okay, I
One
have
question.
yes, go ahead.
The equation 1.38,
Mhm.
you use it to find out which P you want in a construction,
Yeah.
but very technically speaking, this is not a convex combination. Or I don't know. In between, you could get like probabilities that do not add up to one, right?
We show later that they're good.
Okay, okay.
Yeah, so later you will find that actually you can also see it here. In effect, I say it explicitly that P is between
P should be between 0 and 1. That's what they say.
right. So it is going to be because P0 is between 0 and 1, and so this will be between P0 and 1. But you're right. Do I say it explicitly that I think you're right. I'm not saying it. Okay,
I'm not sure
so
if you all you need is like to find the correct expression for P, just like a guess, and we see that it works.
yeah, I
Okay,
think
then this is fine.
so. We should probably make it more explicit. Thank you for pointing it out. So we need to find a P in 0, 1 such that the thing is this.
Yeah, but you say P element 0, 1.
Right. Okay. So now, which means, and now here we
Mm.
have to check that if P0 is between 0 and 1, then also P is between 0 and 1.
Yeah.
And we're not doing it. So if, let's see, is there a quick way to see this? Well, if this is 0, this is 0, this is 1. If
Yeah.
this is 1, this is going to be 1/2. So the extreme are fine. Is there a way?
It's definitely positive, right? Everything is positive, and the denominator is always bigger than the numerator.
Right. It's always positive, and the denominator is always bigger than numerator, so it's going to
Yeah.
be less than 1. Very good. There you go. Let's see. Note that since P0 is greater than 0, uh, P is strictly greater than 0. And since the numerator is always bigger than the denominator, P0 is strictly less than 1. Perfect. Thank you. This is exactly why we're doing this. Not only things
But I
have
think you mean P and not P0.
Oh, yes. Okay, we got it. So note that since P0 is greater than 0, P0 is, let's say we have, okay, and since the numerator is always bigger than the denominator, let's say greater a little bit. Then the denominator is, okay, so good. So we have a good P. And now we can go.
Just formatting wise,
Yep.
I feel like maybe if you have something like P0, there should maybe be just a tiny space to separate them out and not make it look like it's like a PP.
You
Yeah,
mean
that
in the
exactly.
product?
hmm It's a
Uh,
minor thing. It's just it feels like they are one variable rather than two.
Okay, let's. I don't understand why this thing never like sometimes it doesn't find the right spots and sometimes it does to click and see the source. I'll never understand what's going on because it's a pain to find it. In principle, I
hmm
should be able to control click, but a lot of the time you see it just goes to the end of the math sections, but there are some places where you actually click and it actually finds the spot like it did it before, and now it's not finding it. Is it just because I need to rebuild? Is that the problem? When I make a modification, it gets lost? And then also when it builds, sometimes it goes, oh man, it's so annoying. Okay, let's try to find. Now we show, so would be this expression, right? There is a yes, so the last part, uh, No, where is... This is why it's hard for me to see where we are. Oh, this is the part where we are. Okay. And this is the bar B, bar P0. So I think I need to do this.
Yeah, that's a bit better.
To me, it looks weird.
The weird thing I think is that the E now doesn't have the same spacing. Like it should be all consistent, right? You can't
Yeah.
mix it. Not sure if it's worth to go over that right now, but it's just a thing to consider,
Yeah.
maybe, that this is more readable, right?
Yeah, and probably needs to be then consistent over the whole.
Yeah, exactly. But that's, yeah, you don't have to do that right now. It's just
Yeah.
something to think about.
Okay. Okay, so we are here. So we found our P, and now we want to show that what happens to 2PA plus 2P bar E. So we take this and we expand it again so that we have the two PAs, single PAs. And then we can use the relationship that we have for this particular P and write this part as simply P bar multiplying P0A plus P0 bar E. And then we know that the relationship is valid for P0, so we can substitute the A with the B. And now we can re-multiply these terms so that now we have PA plus PB plus 1 minus 2PE. We switch the order of the B and the A, and we take this and we re-expand it in terms of P bar P0A plus P0 bar E. And we have the expression with the correct P. We can substitute A with B. We make the multiplication so that we have PB plus BB, and then we can put it all together, and we have 2PB plus 2P bar E. And so these two are the same. So the relationship then is valid for P1 equals 2P. Note that P1 is greater than P0. In fact, P1, which is this 2P0 over 1 plus P0, let's suppose that it's greater than 0. What happens is that we can take this and put it on the other side. We can multiply, so we have P0 plus P0 square. This P0 simplifies with the 2, and so we have P0 greater than P0 square, which is true because P0 is between 0 and 1. So it is true that P1 is greater than P0. And since now the relationship holds for P1 greater than P0, you can repeat the process again and find that it holds for P2, which is 2P1 over 1 plus P1 greater than P1, and so on. And therefore, since we can find a greater mixing coefficient for which the relationship holds, combined with the previous result, then it must be then PA plus P bar E is equal to, let's go a little bit more up, equal to PB plus P bar E for all P from 0 to 1. Because we can always find something greater, get all the 1 from the back, get something greater, and then in the limit we can get everything that we want. So now that we know that, now we show that if this is true for all p's between 0 and 1, then we also have that p with a linear combination, with a convex combination of a and b plus p bar e is equal to pa plus p bar e, or also equal to pb plus p bar e for all lambda that are within 0 and 1. Okay, so the way...
One thing, so we always find a bigger P, like
Yep.
step by step.
Mhm.
And I guess the limit point is 1.
Yeah.
Or not. So really this sequence goes up until 1. It doesn't have a fixed point below 1.
Yes.
Okay, good.
Yeah.
Yeah, good, makes sense.
And so for any p that you choose, you're going to find something that is greater, and then you know that if it's true for something that is greater, then it's true for it because it's lower than something that that converges.
Yeah, that makes sense. I just wanted to make sure it actually reaches 1.
Yeah, it's because we know that these are always constrained from 0 to 1, and you can always find something that is strictly greater.
Strictly greater, but I could make up a sequence which is like strictly monotonically growing, but never reaching 1. Right? Or not?
Yes.
So
So
if
you're right, this is more than that.
so I need to make sure that the sequence actually, like, which is recursively defined, doesn't have a fixed point, or it really converges, gets arbitrarily close to 1.
You're absolutely right. And this is exactly why we should review the math, as somebody should always review the math that I write. Okay, so it's gonna be true because it's basically, this relationship is equivalent to this, and so you're always gonna get something that it's gonna approach. Is there a simple way to see it? We would probably look at the fixed point of this expression, right?
Yeah. Not sure if it's enough to say if there are no other fixed points, and if it's growing,
Yeah.
it should go up until 1. Kind of makes intuitive sense.
Yeah. It's exactly going to be this. And you see that the fixed point here, 1 is a fixed point, right?
Yeah.
If you put 1, there's
It
2.
has 0 and 1 as fixed points, I think, and that's the only ones. So if you put like 2 p0 over 1 plus p0 equals p0, that's the fixed point, right?
Yeah.
That's 2 and 1, 0 and 1.
Okay. So we should do that. Where should we do it? Okay, here. No, he doesn't know where I am. Oh, what a pain. Okay, so, okay. Okay, so how do we write it? But you're right. So this is great. This is great. We are hammering the math. Note that um, note that 0 and 1 are the, yeah, maybe I have to write 1 are, okay. So we basically want to say that this sequence has a limit and the limit is 1. That's basically what we want to say. We thus have a sequence of elements between 0 and 1, and we need to determine what is the limit of this sequence. The only two fixed points of the expression, let's say f of p equals frac 2p1 plus p are 0 and 1, since we start with an element that is strictly between those values, the series, the sequence will converge at 1, and therefore
Yeah, so the thing there is that that 1 is the stable equilibrium, whereas 0 is unstable or something, right?
Right. I don't know if I want to like write it there as well because
Mm.
so it's I mean we can write it, but yeah, that's basically the thing is the zero is unstable, and so it pushes everything from 0 to 1.
Yeah.
Uh,
So you probably want to write the numerals, right? Not the word. I'm not sure if you want to put 0 and 1 as a word.
like here, you want the number instead of the word.
Yeah, I think so, right? Yes. I'm not sure. I guess it's a
In English, they always like putting the word.
the thing is that you're like talking about the object itself. Like why switch between the word and the symbol if you already have the symbol, right?
I agree. And then when I look at things with my wife, she's gonna tell me that she prefers the. Anyway,
Okay.
let's put this. Let's put this for now, and then we'll see if we get objections. I also prefer that the numbers instead of the words, and yeah. So I think maybe this is in a proof, so maybe it's gonna be okay. Okay, so the only two fixed points of the expression is 0 and 1. We can write it like, and in fact, 0 will be. I don't know if I want to talk about equilibria. I mean, I know what it means. I don't know if everybody knows what it means. Because when you talk about fixed points, do you talk about stable or unstable fixed points?
Yeah, like attractive and not attractive, right? Or something like that. What's the word? What's the technical?
I don't know.
There is a technical term.
So
I'm not
there
sure
is
if
an
it's
attractor, but again, the attractor I always think in dynamical systems.
yeah, but the attractor is a fixed point, right? And specifically a stable one because it attracts everything, whereas the unstable one will push stuff away. Um,
Attracting fixed points and repelling fixed points and periodic fixed points are defined with respect to fixed point
yeah,
iteration.
yeah, attractive fixed point. There you go.
Attracting and repelling. Okay. Okay, so let's just put it then. The only two fixed points are there with 0 being a repelling fixed point and 1 an attractive fixed point. Since we start with an element that is strictly between 0 and bar, the sigma will converge to 1. Therefore, we can always find a greater mixing coefficient from which the relationship holds. Combined with the results, we get this. Yeah, we are fixing the math interactively. Okay, so did this compile? Okay, so we can repeat the method. We first have a sequence of elements between 0 and 1, and we need to determine what is the limit of the sequence. The only two fixed points of the expression fp equals to p1 plus are 0. Should I put x instead of p at this point so that there is no confusion?
Yeah, perhaps.
Yeah, let's put x. Too many p's. There is auxiliary for the expression f of x equal to x, 2x over 1 plus x, are 0 and 1, with 1 being a repelling fixed point and 1 an attractive, an attracting, not an attractive. Okay, an attracting fixed point. Since we start with an element that is strictly between those values, the sequence will converge to 1. Therefore, we can always find a greater mixing coefficient for which the relationship holds, combined with the previous results, PA plus P bar E equals PB for all P between 0 and 1. Are we good? We are good. Okay. Now we show that if this relationship holds for any p between 0 and 1, then it also holds for essentially when the first term is an arbitrary convex combination of A and B. So we can substitute an arbitrary convex combination for lambda with the A or with the B. And this is easy to show because you can just take the relationship with the convex combination. You break it down into the sum of two convex combinations, one containing A and one containing B. And then let's say we change the one from B to A. We put it back together. Therefore, this has only A. And therefore, for what we had before, this is also equal to B. So we can put whatever we want. And so up to now, note that we have not used the entropy. So all of these would be true even for a non-cancellative, would be true for any convex space. But now we introduce the entropy. And what we do is we show that the entropy of a convex combination or of a convex combination of A and B that satisfy what we had before is equal to the entropy of A, which is also going to have to be equal to the entropy of B for all lambdas. So using the entropy bounds, we can set lambda between 0 and 1. We have that the limit of the entropy with when P goes to 1 of the entropy of P, a convex combination of A and B, so a mixture of A and B, plus some other element E, has to be less or equal to the limit of the upper bound. So that is IPP, the Shannon entropy, plus P, the entropy of S, of the linear combination, and plus P bar, the entropy of E. What happens in the limits is that P bar goes to 0, the Shannon entropy goes to 0, the P goes to 1, and so this is equal to S of lambda A plus lambda bar B. And now we look at the lower bound, then the limit has to be greater than the limit of the lower bound. And again, P goes to 1, P bar goes to 0. Therefore, the limit has to be the entropy of the convex combination. Okay, so since we are constraining from below and above, it needs to be that the limit of the entropy of P plus lambda A plus lambda B plus P bar E has to converge when P goes to 1 to the entropy of the mixture. And now that we have this, using the above property, we also have that the entropy of the mixture is the limit of the convex combination with some P and some E. We know that from before, this is equal to the limit to this part inside is equal to PA plus B bar E. This is also going to be the limit of in the limit. This is going to be the entropy. No, sorry. In the limit, yes, this is going to be the entropy of A because P goes to 1 and P bar goes to 0. So this just converges to the entropy of A. But since we can also substitute this with PB plus P bar E, this is also going to be the entropy of B. So we have that the entropy of any mixture of A and B is equal to the entropy of A, which also has to be equal to the entropy of B. And now what happens? By strict concavity, since we have that the entropy of the mixture is equal to the average entropy of what we're mixing, then we have that A and B have to be equal. So basically what's happening physically is that if we're doing these mixtures and we make the limit when we go P equals to 1, we have these bounds from above and below that sort of squish everything to be the same. And then by strict concavity, since they have to be the same, the ensembles that you're mixing have to be the same as well. And so this very convoluted things basically tells us that we have vector spaces. So any physical theory, as long as it has ensembles, then it has vector spaces. And so that tells you that the mixtures, the mixing property plus the existence of the entropy tells you that we are always going to have vector spaces. And all the vector space structure that we have in physical theory come from essentially this argument. So, good. Give you a few seconds to see if there are more questions or perplexities.
So on other spaces, I could not define a strictly concave entropy.
Mhm.
So, and by demanding that we have one, we have to rule out these spaces.
That's exactly it.
Yeah, okay.
Yeah. And so this is one thing, then later we can see something else. And here now I will see an example where you have something that it's not a vector space, and we see that you can't define an entropy on top, or that it gets ruled out by the entropy, that if you didn't have the requirement of the entropy, you could have the space. So very quickly, an element E can be expressed as an affine combination of ensembles with E, where E is the sum of Pi EI. But now P only needs to sum to 1. They don't need to be positive. So an affine combination is where the coefficient sum to 1, but the coefficient can also be negative. So you could have a P that is 2 and another P that is -1. So they sum and they give you something. And you can basically think it like this. You have 2 points. If you're doing a convex combination, you're taking a point that it's in between. If you're doing an affine combination, you're taking a point that it's on the line. And so since we are in a vector space, now we can probably properly talk about affine combination, because there is only one way to extend the line in the direction away from the inside, from the region between the 2 points. And in the same way that not all infinite convex combinations yield valid ensembles, not all finite or infinite combinations, affine combination yields valid ensembles. So you could go out of the space by doing an affine combination. You're not always guaranteed that you can do it. And this idea of allowing for, let's say, negative mixture should remind you of the idea of negative probabilities in quantum mechanics. Because what's happening there is that when you're describing ensembles in quantum mechanics, you don't have a convex, just a strictly convex coordinates. You have a set of affine coordinates, because you don't only have the classical mixtures, you have quantum mixtures that sort of go away from convex combination. But if you allow for affine combination, if you allow this negative coefficient, you can basically always cover the whole space. So that's the trick that you're doing in quantum mechanics with negative probability. You are essentially using affine combination instead of convex combination. So that's how it works.
Are you thinking about these Breit-Wigner functions or something like this?
Yeah, there are the Wigner function, and then there are there's the Wigner function, the Husimi function,
Yeah.
the other guy's function, and then in when you are in finite dimension, so let's say that you have the block ball, you can actually take, it's a ball, and so you can take 4 points, right? Then make a triangular pyramid and have either have this pyramid inside the ball, right? And so you can get the parts that are not inside the pyramid by having negative coefficients, or you can make the pyramid outside of the ball. And then you can reach all the points with convex combination, but not all the convex combinations are going to be inside the ball. Some of them are going to be the points that are not going to be included. And also that's another way that people parameterize the space in quantum mechanics.
That's what's it called? Positive operator valid probability measure or something.
I don't remember the name.
POVM.
It's
Well,
projection operator value measure. It's something else.
yeah, it's something else. Yeah.
Oh yeah, no, I thought about the pyramid thing, like the tetrahedron. That's like whatever, doesn't matter.
They might do it. I mean, I know that when you're doing things in quantum information, sometimes you use these coordinates. I just don't know how they're called.
Okay.
Yeah.
Coming up in cubism, I think.
It could be. So the point is that looking at things like this, it gives you a direct understanding of what you're doing in quantum mechanics when you're using the negative probabilities. Like they're not probabilities; they're just coordinates that you're using in the vector space, and you can always do it because you have an affine space, so you can always do it, and it's useful and convenient for doing some things. But you shouldn't, you should be skeptical of putting an ontology on these things and thinking that they're real things. I guess that's kind of the issue. So the thing that I have not yet proved, and it's an open question for me, is whether the space not just embeds in a vector space, but in a topological vector space. So it is still an open question whether the ambient vector space must be a topological vector space. Axiom of ensemble and mixtures are not enough to guarantee the topological nature of this vector, of this vector space, of the vector space. And see this post in this math exchange question. There is a counterexample that if you just have let's say a topologically convex space that is cancellative, it is not necessarily embedded in a topological vector space. And the issue is that we have no guarantee of continuity on the inverse. Basically, you can do the substructure and multiplication by a negative number, and the continuity of the convex structure is not enough to guarantee that you have continuity on the vector space. But as is shown later, the entropy provides a pseudo distance, which allows one to create open balls of the space. And moreover, the entropy induces a metric tensor, which may induce a suitable topology. So I'm sort of 100% sure that this is going to work. I just don't know the details yet. And once you have a topological vector space, there are a lot of things that you can use and so on. So that's basically it.
Is it even a unique embedding? Like, is there one vector space where I can embed my convex space into?
Up to, a linear transformation, yes.
Okay.
So more. So one of the things that you're not going to get is the origin. So the origin is, of course, undetermined. And so it's kind of like more an affine space than a vector space. But again, minus these things, the important thing is that the linear combination is the convex combination. So that relationship is fixed.
Yeah, I was just wondering if we have some freedom to choose, and then we can find one that is continuous in a sense.
Yeah, I know. Yeah, you have to show that it's embedded, that it's continuous. I don't think you can fast because what happens is that the coefficient p become the coefficient of the linear combination. So whatever topologies that you put on those p is going to be then the topology that you have on the everything. So I don't think you have a lot of freedom to change things.
Yeah, makes sense.
Yeah, but again, it should be that the space is metrizable because we are putting we're going to put a metric tensor on it. So there is going to be a distance. So therefore, it's going to be metrizable. And I think so. We are going to have a topology. The topology is going to exist. Its topology is going to be metrizable. I think at that point it has to be a topological vector space. I don't think there are many other choices. So again, it's just a matter of doing the due diligence and make sure that these things work. Now, the thing that is interesting here is this example where I have, as an example of a convex space that is non-cancellative, that does not embed in a vector space, and therefore is ruled out as an ensemble space, we consider one in which the convex combination of two different elements returns always the first. And we show that this can be made to satisfy the axiom of ensemble and mixture, and therefore it really is the axiom of entropy that rules it out. And again, it's one of those abstract mathematical game that we play to make sure that the axioms are, what the axiom are actually doing, so that we know what's going to happen. So self-mixture. So let E equals the set of A and B be a set endowed with a convex structure that satisfies the identity, idempotent, and commutativity, and such that PA plus P bar E equals A if P equals 1 and B otherwise. So the ensemble space is made of only two elements, right? And if we mix A with A, we get A. If we mix B with B, and we mix with B. But if we mix A with B, we get A if we are doing 100% probability of A, and we get B in any other case. So as long as there is a little tiny bit of B, then we get B. Okay, of course, physically you'd say this is nonsense, but the problem is like, is it ruled out? And that's kind of the reason, like the entropy rules out this case. So identity, idempotent, and commutativity are satisfied by constructor. And for the associativity, note that the final result of multiple mixtures is A if and only if all elements of the mixtures are A. The order does not matter, and therefore associativity is satisfied. Therefore, such structures satisfy at least the axiom of mixture without a requirement of continuity. So this horrible thing is mathematically a convex space. And now we say, can we put a topology at T0 cycle counter topology and make the sum continuous? So for continuity, we need to look at the inverse image under the mixing operation. Note that the inverse of the mixing of the empty set is the empty set. So the only way that we can have nothing is by not mixing anything. The inverse of the mixture of the ensemble space is all possible mixtures of everything. And since the empty set and E must be in the topology of E, then the continuity condition is satisfied for this set. So the inverse image of the full set and the empty set are indeed the full set and the empty set, and therefore everything is continuous for this. Next, we have to look at the inverse image of A. And the only way that you can get A is by mixing A with any coefficient from 0 to 1. So these are all the possible ways that we can mix and get A from A. Or we could mix A with B with coefficient 1 and B with A with coefficient 0. So these are the only way that we can get A through a mixture. And note that 0 and 1, these two sets, are not open sets, they're closed sets. Therefore, A cannot be in the topology of E, or mixing would be not continuous, right? Because the inverse image of A would not be an open set, and therefore mixing would not be continuous. But we know that mixing A is continuous, therefore the singleton of A cannot be in the topology. That's not an open set. Finally, you can take the inverse image of B, and the way that we can get B is by mixing B with any coefficient, or we can mix A with B with coefficient from 0 to 1, or we can mix B and A with coefficient from 0 to 1, again with the 1 included here and the 0 included here, and the 1 and here and the 0 here excluded, because that would give us A. Now we can re-express this set, right, with this union of sets with we can basically say that we get B whenever we mix B with anything with coefficient between 0 included and 1, or B with anything in the opposite order with the coefficient from 0 to 1 where only 1 is included. Now, the half open set 0 and 1 and 0 and 1 with the opening on the other side are both open sets of the interval between 0 and 1. So B can be an open set. We would be able to make it continuous. And since the topology must be T0, then we must include at least B, and therefore the topology would be the empty set, B, and the full set, which is a T0 second countable topology for which mixing is continuous. So this means that the ensemble before satisfies both the axiom of the ensemble and of mixture. So in principle, if we didn't have the axiom of entropy, we could go and create this crazy thing and say, oh yes, this is an ensemble space. So it is therefore the entropy that rules out this case. If the entropy of two ensembles is different, it would jump from SA to SB for an infinitesimal mixture, which violates the upper bound. And we saw before in this example, if we have A and we mix it with a little bit of B, we jump from B. And so the entropy would have also to jump. So if it's by continuity, it can't jump, so it would have to be equal. But if the entropy of A equals the entropy of B, the entropy of the mixture of A and B is also the same, so the two ensembles cannot possibly be different by strict concavity. So this is exactly how the mechanics of the math rules out this case. And intuitively, this tells us that we cannot have a mixture of two different elements that happen to be equal to one of the original elements. So we have this corollary that A and B be two ensembles such that PA plus P bar B equals B for some P between 0 and 1, included with the 1, then A has to be equal to B. And this is just a silly consequence of the non-cancellative part, because we have PA plus P bar B equals B, which is also PB plus P bar B, for some P included from between 0 and 1. So we're mixing something with two things with something else, and these are equal. Therefore, A and B have to be equal. Okay, so this really tells us that these bounds on the entropy and the continuity on the entropy makes the space nice, and it's ruling out this degenerate mathematical case that we would have in convex spaces, which is nice. Let's see, do we have, so I don't know that, no, we can try. So the other part the other constraint that it's, as I said, it took me like a year to figure out is whether we now know that we are in a vector space, right? And so we know that we have an ensemble space, which is a subset of a vector space. We're going to have 2 points, and we can get a line between 2 points. And now the question is whether this line can still be, it has to be finite, can be infinite on one side, or can be infinite in both sides. That's basically what we can show here. And we show that the line have to be bounded. That is, another constraint that the entropy imposes is that every affine direction is bounded, even if there are no endpoints. So you could still have an open interval, but that open interval in the vector space has to be a subset of a compact, it has to be bounded, essentially. That is, if we take 2 ensembles, these identify a line that contains all the affine combinations in the vector space. The elements of that line that are also in the ensemble space are contained in a bounded segment of that line. And this is the figure. E is the ensemble space, and V is the embedded vector space. Taking 2 ensembles, the dashed line represents all the affine combinations. Those that are in the ensemble space are aligned as defined above, as undefined below, because the thing is... Okay, so let's see where we get. So we call a line A is a subset of the ensemble space, a convex subset such that for any 3 elements, one can be expressed as the mixture of the other 2. So I take 3 elements of the ensemble space. Well, either this one is expressed in terms of the other 2, or this one is expressed as a convex combination of the other 2. So we have A1, A2, A3 in A. There exists a permutation that takes 1, 2, 3 and puts it to 1, 2, 3, and a P such that E of sigma 1, so one of the element, is equal to P, the second element, plus P bar, the third element. And so basically it gives you a line segment that it's inside the ensemble space. And we will want to show that these lines are bounded, that there is a bounded interval, an open, a bounded interval. The interval is bounded where we're putting that line. Given A and B, there is only one line that connects them. Since an ensemble space embeds into a vector space, given two ensembles, there is only one affine line that connects them. A line is the intersection of the affine line with the ensemble space. And again, there is the ensemble space. You take a line and you chop it at the extreme of the ensemble space. That's the idea. And now we have to show that the lines are bounded. So let A be a line. Then we can find a bounded interval V and an invertible function from that goes from the line to the vector space, such that the convex combination becomes the linear combination for all A, B in A. This is what we want to prove. And the way that we're going to prove it is going to be more clearly explained by looking at this picture. So if you imagine that we have a line, we are going to have 4 points here. We are going to have 3 points that are given, and these are also going to have a given entropy as well. Right, so you imagine on this coordinate is going to be the coordinate of the point along the line. And on the vertical axis, we have the entropy, right? So this would be the first point with entropy 0. This would be the second point with an entropy a little bit more than 1.5 and so on, right? And so the idea is that given 3 points, we want to be able to add a 4th point. And we want to see how further out we can put that point. Now, to put this point here, now it's clear that this point has to be below this straight line because the function has to be concave. And so if this point were above the line, you would have a convex function instead of a concave function. And since the entropy is strictly concave, then this point has to be strictly below the line. Okay, so we have one constraint on this point. This point has to be below this blue line. Another thing that needs to happen is that this point here, right, is going to be able to be expressed as a convex combination of the first point and the last point that we want to add. So if you imagine the entropy of this point as calculated, from the entropy of these two, this has to be below the upper entropy bound, right? So this is exactly the average entropy between the two plus the Shannon entropy between the two. So this point has to be inside here. So we can't put these green points wherever we want. We have to put it in such a way that the curve that it's above the upper bound is always above the second point. This purple line becomes the constraint on the green point, such that the Shannon entropy, the upper variability bound, is always above here. So if we put this point below here, then we would have an upper entropy bound that would be below this. So we can't put the green point below the purple line. The green point has to be above the purple line. And then what you see, of course, is that these two lines intersect. So if we want to put a green point too far, right, we ran out of space. We can't assign an entropy that will satisfy the strict concavity between the last 3 points and the upper entropy bound between the first, the second, and the 4th point. So that's intuitive, the proof. And that's why the things are bounded. And now the math in the proof is just a mathematical expression of this geometrical fact. Okay? And this is how I proved it. This picture is from Desmos, the sort of the graphical calculator online. I started putting points and I started moving things around. And then I found the right combination of things, and then I cleaned it up. And this is how it turned out. And as I said, the problem that I had proving this is that I was doing everything with 3 points. And it's when I realized that I needed to add a 4th point and have these different combination of bounds that the proof came up. So, okay, so let A be a line. Pick E0 and E1 in A. For any A in A, we can find a convex expression between E1 and E0 and A. And rearranging the terms, we can always write A as x bar E0 plus x E. Oh, this is, we can write not a convex expression, but an affine expression. Okay.
So in your drawing there, the blue point is A and the red point is B.
In the drawing, it's going to be explained later. So we're going to have 3 things. We're going to have 0, A, and B. So this would
Yes.
be 0. This is going to be A, and this is going to be B.
Yeah, okay. Apparently, there is a AV desync. I just noticed, but yeah, that's fine. Yeah.
What?
Where you basically, you already pointed, you already said this is going to be A and we're still pointing at 0 like this. The delay was exactly as much as it took you to draw the mouse from here to there, basically. Well, it doesn't matter. I understood. I think the graphic, I guess this isn't the final one. It definitely should have the labels and probably should have the 0 points pointed out especially as well, because right now, I mean, it's the origin, right? But it's not explicitly drawn as one of the points. So that should also happen, I think.
Yeah, I agree. I mean, all the drawings are,
Yeah.
very, very temporary. At some point, they need to be filled in. Yeah. I figure that a non-final drawing is better than no drawing.
Yeah, for sure. That's fine.
Okay, so the first part we are just setting up.
Did you fix the thing yet? You wanted to fix but the fine thing?
Oh, yes.
I distracted you, sorry.
Yes, for any A, we can find an affine expression between E1, E0, E1, and A. Rearranging a term, we can always write that A is equal x bar E0 plus x E1, where x is in R at this point, right? This is not, it's an affine, it's not a probability, it's not a mixing coefficient. Note that x uniquely determines A. Therefore, we can define f of A goes to x and will be an invertible function. We can verify that given A and B, we have that this function applied to a mixture of A and B. We can now write this is going to be, whatever elements that we have here. So we're going to have p x bar, A is going to be, we can express it like this. So A is going to be p x a bar E0 plus p x a E1, and we do the same thing for B. So we expand B as xb bar E0 plus xb E1, and we get the coefficient. So this is just substitution based on this. Then what we do is just group the terms with x0. So we have p x bar A plus p bar x bar B E0, and the same thing for E1. And now we go and look at the definition of A. The definition of A is just taking the coefficient from E1, and the coefficient of E1 is simply pxa plus p bar xb, which is exactly pfxa plus p bar fb. So this is a map that preserves the convex combination that become linear combination on the map. We're going to show that the image f of v of f of A must be a bounded set, or it would eventually violate the entropy. bounds. Given a value of x in V, there will be an entropy value S given by the inverse of f of x. So x is just a real number. You get an ensemble, and that ensemble is going to have an entropy, which we can write as a function of the real value S of x. This function will need to satisfy continuity, strict concavity, and the upper variability bound. So now we turn the problem, instead of looking at it in the ensemble space, we're just looking at it on a real line and a function of a real line. So we're going to show that the function f(s) of x cannot extend to plus infinity. The same argument can be applied by symmetry for minus infinities. And we're going to assume that s of 0 equals 0 without loss of generality. If s is not defined at 0, or if the value is different, we can apply a translation of the argument or on the value, which will not affect the concavity of the function. So we make our calculation easier. Okay. So now let 0 strictly greater than a strictly greater than b in V be two distinct values with S of A and S of B, their respective entropy. We're going to show that if we pick a C greater than B sufficiently large, we're not going to find a value for S of C that satisfies the bounds. In this picture, we have the 3 points, A in blue, B in red, and C in green. The horizontal axis represents the value, the position of the ensemble along the infinite line, while the vertical axis represents the entropy. Consider the points A, B, and C. Since the entropy is strictly concave, C must be placed under the blue line, which represents an upper bound on S of C. Now consider 0, A, and C. Since A is the mixture of 0 and C, SA will need to satisfy the upper bound given by S0 and SC. In the diagram, the green line represents the upper bound on S of A for the specific choice of C and SC. And since A and SA are fixed, this puts a lower bound on S of C, which is represented by the purple line. That is, the purple curve represents the minimum value we have to assign to S of C, such that SA still satisfies the upper bounds between 0 and C. As the picture shows, the two bounds meet at some point and cannot be satisfied. So this is the same explanation that I told you before. It's he's here visually, and at some point when we make this document final, this is going to have axes, it's going to have symbols on top and all that. And if somebody wants to contribute that diagram, or maybe I can just ask ChatGPT to make diagrams. If I could give the template of the drawing to ChatGPT and then it would give me the latex that generates something similar, that would be amazing. I don't know if we're there yet. So from strict concavity, noting that C minus B over C minus A plus B minus A over C minus A is equal to 1. And you can see that this is equal to 1 because if you sum them, the B goes away. You have C minus A over C minus A, and which is 1. We have, so S of B is equal to S of S of C minus B over C minus AA plus B minus A over C minus AC. Okay, and if you do the calculation, while the sum of these two coefficients is 1, the sum of these two numbers is actually B. And the way that you can see it, if I remember correctly, and let's see, how do you see it? Oh yes, if you multiply this by A and this by C, you're going to have an AC here and a minus AC here. And so those are going to go away. And you are left with BC minus BA. And so you have B times CA, C minus A, the C minus A goes away, and you get a B. So this is equal to this. And so we can see B as a convex combination of A and C, which by strict concavity always have to be greater than the coefficient multiplied by the entropy of A plus the other coefficient multiplied by the entropy of C. Now what we do is take this on the other side while multiplied everything by C minus A. So you have b minus a s of c, and then you have this term multiplied by c minus a, and then this term without the c minus a, and since we brought it on the other side, you get a minus sign. Christian Lascu says, we're studying similar things and need to talk. Huh? In what context are you studying similar things? I do not have a Snapchat, but you can find me on email. So, shoot me an email and then we'll arrange something. Okay, this is the delay of the chat always. I'll continue the proof. Okay, so we show that this is always less than this. And then what we do here, it's a little bit more of a trickery where we have this C minus B and we break it up into a C minus A and a B minus A with the correct with the correct signs. And then what we're gonna do is we can take the B minus A and put it down. Note that this C minus A are the same, so we can collect it. And so this S of C is less than S of B minus SA divided by B minus A multiplied by C minus A and with the sum of SA. This is basically a line. Like this is a linear interpolation between SA and SB, and this is the blue line that we had in the graph. Oh, in gravity, some things like this? Oh, you mean a connection between gravity and entropy? I'm absolutely interested in connection between gravity and entropy because I know that has to be one, but I still don't understand how it is. So, okay, so this is the upper bound. And now we do the other one from the upper bound and noting that C minus A over C plus A over C is equal to 1. And again, it's easy to see because minus A and A go away. You have C over C and you get 1. And recalling, we assume S0 equals 0. We have SA. And again, we can now express SA as a linear combination of 0 and C. And this is very easy to see because this is just 0 and this is just A. So clearly A is equal to this. And so now we have A is a convex combination of 0 and C. And this always have to be less or equal to the upper bound. So this is the Shannon entropy between the coefficient, and this is just the first coefficient for the entropy of 0 and the second coefficient with the entropy of C. Now, of course, this is 0, so this goes away. And we're going to take this and bring it to the other side. So we have this term is greater or equal to S of A minus the entropy of the coefficient. And we take A and C and multiply it on the other side. So this is now a bound that SC has to satisfy. Okay, and this would be the purple line. The SC has to be greater than this. And this, if you plot it, is the purple line. Now, combining the bounds, we have that this one was greater than SC, and SC has to be greater than this. So this, which is here, has to be greater than this. So we put them together, and now there is just math trickery that goes on. We take all of this and multiply everything by B minus A. So this is just the first term. This is just the second term. This is the third term. And here we're sticking a B minus A here. And here we're just rewriting the minus and the coefficient and the B minus A. So this is just basically rewriting. Now we're going to take these two, and there is a B minus A and C minus A. We put them together, and we are also multiplying everything by A. So this is going to be C minus A times A for SB. The B minus A and C minus A with the minus simplifying into a C minus B, and we're going to have the A. And here we're just copying the terms that we had above. Then here we can take this and bring it over the other side and make all the multiplications. And the other terms are unchanged. Now we collect elements here. The AC and the AC are going to go away. So we just have a B, C minus A. And here we have what we had before. Note that the C minus A and C minus A here match. So we can divide everything by C minus A. So we have that A S of B minus B S of A is greater than this bound, that C B minus A, C minus A, and the entropy of the coefficient, the Shannon entropy. Okay, so this has to be always satisfied if we want to be able to extend the line. So for any C that we have, these things would have to be satisfied. Now, since B is greater than A and C is greater than A, and the entropy is always a number that is greater than 0 because P is strictly between 0 and 1, the right-hand side of the inequality is always negative. This part here is always negative because all these elements, C, B minus A, C minus A, and the entropy are all non-negative. So this has to be negative. As C increases, the right-hand side will go to 0 because a limit of C that goes to infinity of C of this element, this is simply going to be B minus A. And if we make C goes to infinity, well, this is going to be 1, this is going to be 0, and therefore the entropy is going to be 0. And note that the left side instead is a constant. So if the constant is positive, then the inequality is always satisfied because we would have a positive value always greater than a negative value or 0. So that's fine. If it is negative instead, it will not be satisfied for all C. If this is negative, since this is going to increase to 0, at some point this inequality is not satisfied anymore. And so from strict concatenativity, noting that B minus A over B plus A over B is equal to 1, and again, you can just see that minus A simplifies with A, B over B, and so you have 1. You have that SA is equal, again, S of B minus A over B 0 plus A and B. So we can express A as a convex combination of 0 and B. This, for the strict concavity, always have to be greater than the average of the entropy. The entropy of 0 is 0, so this has to be greater than A over B S of B. So we take B on the other side. We have B as A always have to be greater than A as B. Therefore, 0 is greater than A as B minus B as A. Note that this is exactly the left side of the inequality. And this shows that the side of the previous inequality is negative. So we saw that this is negative. Therefore, this term is negative. So we have something negative here. And then you are going to find a C for which the inequality is not satisfied. This shows that the left hand of the previous inequality, and therefore the bounds cannot be satisfied over the whole R. This means that V equals FA must be bounded, and therefore every line is a segment as embedded in the vector space. Okay, so that should be it. That's the proof. And there is a remark here. Note that this does not mean that along each direction the line is closed in the vector space. That is, it may not include the extreme points. It could be an open interval in the convex space. An open bounded interval, in fact, is still a convex space, and we would be able to define an entropy of it. Whether there are other reasons why the extreme points are in the ensemble space, I still don't know. So for now, I'm open to the possibilities of ensemble spaces where the extreme points are not there. But still, even if topologically is an open set, as embedded in the vector space, that sort of open interval without the endpoint is still an open interval, finite interval, not infinite interval, infinite set, whatever. Okay. So that proves what it took me at least 1 year or a year and a half to figure out. It's one of those problems that I kept going back, every 4 to 5 months, and I would bang my head on it and not able to prove. But now we have it. In talking to one mathematician, also told me that if this is the case, then you can make this and see that this is a cone on some other linear space, which I don't remember. I still have to understand. But anyway, this supposedly the fact that all these lines are bounded gives you much nicer math to work with. So that's basically what I wanted to look at today. And again, these were the entropic constraint on the space. The fact that the entropy exists fixes a lot of stuff. And then next time we're going to look at the geometric part that the entropy gives us. And so I'll open up for questions if there are any questions. Otherwise, we can stop.
Nice work.
How much are you saying with this? Like it's the embedding is, you said, up to some linear transformation. You only say the interval is like it's bounded. So does it make the convex space compact in some sense?
Yes. The convex space is basically, you can say that any ensemble space is a subset of a compact set in a vector space. That's what you can say.
Yeah, okay. Yeah, that's pretty good.
Yeah, exactly. It's pretty good. And again, I like the fact that we proved all of this from these simple axioms that we can justify from the physics. And it's one of those things I wouldn't expect that you can get so many things out of those axioms, but you can actually even get more, as we'll see.
Yeah, that's very cool.
So one technical thing in your proofs, before I know that I can embed my convex space, I only know what so convex combination has two coefficients and they add to one, right?
Yeah.
I don't even know. I can, in general, there might even be combinations, like linear combinations with three coefficients in the very general case, that add up to one and they're all positive.
Mhm.
Oh, wait, then, but even then, I'm not sure if this exists, right? Does that make sense?
So if you know that you can make a convex combination of two elements, you know that you can make convex combination of any finitely many elements.
Yeah, I would kind of expect this.
Yes, so that's if you recall, let's go back to the axioms. Okay, so the fact that you can have that you have associativity and commutativity means that you can write the convex combination of more than two things.
As long as everything in between is also always like between 0 and 1, like all the probabilities that show up in between, right?
Yeah, the convex combination is always defined where all the coefficients are non-negative and they sum to one.
Yeah, okay.
And if you write this, you can always, since, the third or any of these is going to be 1 minus the sum of the other two, right? So
Yeah.
P2 is 1 minus P1 minus P2. And then you can write things in this way, and these are the way that you need them here to do the associativity.
Yeah, that makes sense. I think one step, there was one part in your proof where I wasn't sure if your probabilities leave like the 0, 1 interval.
Mhm.
even though like in the total thing, everything adds up to 1.
Yeah.
That
So
would be a problem, right?
right, right. So it's magic in the sense that as long as you have, three things, right, and you combine them in some way where you define one part to be a number, like a number from 0 to 1, then you know that the other thing is going to be exactly one minus the other, one minus that part. So that there are a lot of times where let's see, in some proofs, I only care about looking at one side because the other side is always guaranteed to do the right thing. So when I'm here, right, you see,
Yeah.
I know that this is 1 minus 2p because the sum of these two is 2p, right? And
Yes.
when I rewrite this, well, I know that this part is my p bar times something else, right? And then I kind of don't care about like this is a bad example because I define that p to be something specific. Let me see if I have
I
if I
was wondering if p is like above 1/2 and you have p plus p, it could get above 1. And then you kind of cancel it by 1 minus 2p, which then could be negative for some p's.
right no, because what happens is that whatever coefficient you are factoring in it's going to become the division of the other thing and it's going to renormalize the
Okay.
rest of the coefficient.
Okay.
So the whole thing of renormalization, right? This keeps whenever you're making this, you're basically always renormalizing this sum. I'm trying to see if there is a proof where I actually probably it's probably going to be in the mixture. Wait, it might be here, for example, right? When I do these crazy things, right? And so here. Right. So here I have this thing, and then you see here I am essentially summing and subtracting apart, right? And then when you see, I'm summing as I'm subtracting here, and when whenever I'm doing these, even from here to here, the only thing that I need to look at is sort of one side. The other side is going to fix it by itself, essentially. I don't, I can,
Sure.
but I should make you know what? Let me make a to do because that's something that even a math student that sort of looked over some proofs was, you know what? In fact, I should look at the proofs that he looked at. He looked at the part of, let me see, of yes, so the fraction capacity, where I was making some weird things. Yeah, I don't remember, but he had the same doubt. And
Hmm.
so I should, whenever I talk about here should be the where I should do it. To do in the previous math section, show how when we are arranging convex combinations, you can essentially only look at one side and the other side will always fix itself. So I need to zone in on a nice example that I do something strange and then and then I can show you that again the coefficient go and sum to one, and they do all the things that they expect. And it's probably just a remanipulation of these things, right? Because these things look awfully complicated, right? Here when you're doing
Yeah.
these things, right? And They always work out.
Yeah, I mean, the last coefficient will always be fixed, right? By the other ones.
Yes, the last coefficient is always be fixed.
Yeah, I'm worried whether if one of these coefficients in between becomes negative or bigger than one,
Yeah,
that I'm not sure whether this is still well defined.
yeah.
Yeah.
Yeah, so there are essentially two things that interact with each other. The renormalization, the fact that you are dividing something for another coefficient, and the fact that as you said, the last term of the sequence always has to be the one minus the other, like the complement.
Yeah.
And the two things combined, because if you have a sequence of seven, right, and you say, okay, let me break this into the first three and the second four, right, you're summing the first three, right, and then sort of renormalize on that, right? You basically each coefficient now at the beginning has to the total has to be the sum of those three, and then each of them has to be divided by the sum of those three, right? So that the sum is equal to one. And then on the other side, you have the sum of the four, but the sum of the four is one minus the sum of the other three, right? And then each of them has to be divided by the sum of the last four, but the sum of the last four is one minus the sum of the first three.
Okay.
Right. So these are the things that sort of go and magically fix each other.
Okay, because you kind of recursively define it always in terms of two.
Yes, because you can
Yeah.
always recursively find in terms of two, and you have this associativity property.
Yeah. Okay.
Right. So it's a lot harder to see. It's basically, as you say, as we said before, everything is going to embed in a vector space anyway. So basically, you're just doing linear combinations, right? So of course, everything is going to work out. But you have this constraint that everything has to sum to one, and everything has to be greater than zero. And so that's what makes the math complicated to look at. And it gives you that vibe. Like, how is it that we're always satisfying those conditions, right? But the thing is that whenever you're making a step and you're grouping things, you're always keeping those linear combination, convex combinations, so everything works out.
Okay. Yeah, I mean, once we have the vector space, it's fine. But since you were proving that we can embed it, it's like,
Yeah,
of course, we first need to be very careful.
yeah, exactly.
Yeah, okay.
And the thing that it's magic about the convex combination instead of the vector space, the linear combination, is that since all of the coefficient has to be non-negative, you it's like there are some objects are more important than others. So when you if you imagine just having a plane, right, in a vector space, right, there are no privileged direction in the vector space. You can go any direction can be a basis. It doesn't matter. But in the convex combination, since at some point you stop when you go from one side or the other, right? Because your coefficient cannot go lower than zero. There are some elements that are sort of more fundamental, more important. And so when you're creating a basis of these spaces, you really get extreme points. You really get the things that are, in a sense, objects that are more important than ever in the space. And that sort of makes the convex space behave in a totally different way. Even though it's embedded in a vector space, it gives it a completely different flavor. And it's the idea that if you have probability distributions, right? Whenever you take two probability distribution, you sum them, but you can't always subtract the one probability distribution from the other, because at some point, you can't go negative. So you can only you can ask yourself how much of this distribution is inside the other distribution. With a vector space, you don't have that question, because since you can go negative, you can keep can keep adding or subtracting, and you can have as big or as small of a component inside another vector that you want. So
And those are extreme points, right? Like,
Yeah, that would be
that's
the
pure states.
Yeah, that would be the pure states if you have them. But in an infinite dimensional space, you're not going to have extreme points in the same way. But you still have this bound in when you're making a convex combination between two elements. Yeah, I find these objects completely fascinating. So questions, do photons move? Depends on what you mean by move. I mean, they propagate in space. I think you say propagate. I don't think you say move for some reason. So the photons are excitation of the electromagnetic field and they travel around. In fact, it's the opposite. They can't stay still, right? They always have to move. Okay, so we close it and see you next week for entropic geometry. That's also very interesting. Okay, so I should stop sharing. And bye to everybody.
Bye.
Bye.